One rather interesting aspect of this model, this loss of inertial mass, is we finally end up with a physical explanation for the cosmological redshift. The energy content of a photon produced by an electron dropping from one energy level to another is dependent upon the intensity of the electrostatic field that the electron must drop through. The intensity varies the inverse square of the distance to the nucleus, ignoring the center of mass variation between nucleus and electron relationship above for conceptual simplicity. But as an electron moves closer or falls towards the nucleus due to the loss of inertial mass of the electron, the electrostatic field the electron's orbits through becomes more intense. This increases the energy content associated with each of the orbital energy levels available to the electron within the atom. This more intense orbital field allows the creation or absorption of higher energy photons when the electron falls or rises between orbital fields. A photon with more energy has a shorter wavelength or is bluer. There is no addition or creation of energy to the system since the energy imparted within the more intense electrostatic field is due to the electron falling within the electrostatic field. So, the loss of inertial mass will result in photons that appear bluer today than they were in the past. Since we assume our local measures of wavelength of a photon are unchanged, the wavelength of a photon in the past is observed to be longer or redder than a similarly produced local photon. So the cosmological redshift is being produced, but the observable part is being produced because of the effects of unobserved space causing our spectra to be bluer in the present and makes past relationships appear to be redder. Now, let's see, energy variation over okay, but here we're the energy of a photon in the past versus the energy of a photon produced in the present. So the energy imparted to the photon would vary to the 1/3 power. So the energy of a photon produced in the present would be greater because of this electrostatic field right now. Remember, we're just considering the effects of observable space right now. We're not adding the effect of observable space, just effects or relationships due to the unobserved space, this loss of velocity or the loss of inertial mass due to the change in velocity along the unobserved dimension. So now when we go through this relationship and we get the cosmological redshift, and now when we go through the energy of a photon in the past versus comparison to the future, we know that the cosmological redshift is equal to t to the 2/3 power of time. Well, this is exactly the same that matches the stretch of observable space. So by incorporating this loss of energy along the unobserved dimension, we are now resulting in a cosmological redshift that matches the expansion of observable space. We're now getting a cosmological redshift so the pieces of the puzzle are starting to fit. This is kind of remarkable that now this predicted change in wavelength due to the collapse of electrical orbits is now allowing us to get a cosmological redshift. Also, the other thing that's happened is that there's now equivalency between matter and energy, radiant energy. That E equals mc squared is no longer. I know I have that problem where I took 1 gram of matter, converted it to energy, and I had another gram of matter that stayed where it was. I shot it into space. When the light comes back and I convert it back to energy, there's energy lost. Now the intrinsic energy of a gram of matter also diminishes over the course of time, since its velocity is diminished. That the intrinsic resting energy of the mass is diminished, and when we go through the energy of a photon, it varies as determined previously, the inverse ratio of time. But when we do it now for E equals mc squared, it also diminishes at the same proportional rate. They are both losing. A photon traveling through space and a gram's worth of energy traveling through space and a gram of matter all keep their proportional relationship over time. One of the fundamental issues that exist in the previous model is now resolved. Now, one of the consequences, going onward, we got shrinking rulers and faster clocks. So, and now the effects of observable space were canceled out, but the effects of unobserved space won't cancel out. So, since the radius of an atom was predicted to vary by this relationship, that means with rulers that are composed of atoms would vary by this measure as well. So, objects observed in the past would appear bigger since we're using a locally smaller ruler. And this is just based on the relationships of observable space. Now faster clocks and time dilation is restored. Now when we consider the orbital relationship associated with unobserved space, we end up with exactly the t to the 2/3, so it's matching the same relationship we expect to see with this stretch of space. So this is restoring the relationship of time dilation, and it's directly in proportion to the stretch of space, which is all the pieces a puzzle are starting to fit back together again. As horrific as it seemed, this I determined what the radial acceleration is. It's very small, and it's, you can see it varies the inverse square of the age of the universe. So this acceleration, this collapse of the orbital relationship, is nowhere near enough to explain the dark matter required to maintain the orbital relationships observed within rotating galaxies. But in here is a series of some of the equations, and now I'll call a break right here.